Good afternoon, everyone. My name is Kayhan Batmanghelich. I'm assistant professor in electrical and computer engineering. So I want to talk about intraoperative ischemia. Intraoperative ischemia happens during the reduction of the the flow to blood during the surgery. And if it goes undetected, it results in a stroke. Every year, 500,000 people in the US suffer from a stroke if you combine across multiple types of surgeries, and way more than that during the ischemia. As a result, only for very high level of risk type of surgery, we monitor the EEG during the surgery. So today I'm going to talk about a specific type of surgeries called carotid endarterectomy, CEAs, where in CEAs, is a surgical procedure to remove the plaque from the carotid artery. So during the surgery, the clamp is placed, which reduces the blood flow through the brain, that increases the chance of the ischemia. And as a result, the EEG is continuously monitored during the surgery. So here is an example set up. This is a neurophysiologist on the top in a different room, and this is the operative in an operating room that monitors the process. If they witness some abnormal behavior in EEG, they may inform the surgery operating team. Sometimes that involves placement of the shunt to recover the blood-brain flow. However, this process is a little bit problematic. One problem is that this manual monitoring of the ischemia is very tedious, error-prone, and non-standardized. And to add to that, the access to neurophysiologists is actually not that great. And this is one of the reasons that we only focus on a subset of the surgeries that with a very high risk. So here, the idea here is that can we augment the behavior and the performance of this person that sits in the scanner, the operative, so that the overall behavior is comparable to performance of the neurophysiologist. Here's an example set up. EEG is processed by both AI model and the technicians at the same time. AI generates probability of the ischemia, but also the uncertainty and some of the perimeter of the decision making. The technicians also monitors at the same time, and there is another AI models that monitor the behaviors of the both and make a decision such that the combined model performs the best. The models on the top has been trained on 800 patients from the UPMC hospitals, and the models at the bottom is trained specifically for each operator separately. Here's an example of the result. So I'm showing precision recall. This is the result of AI alone, and each of these curves represent the result of AI and hybrid models together. And you see that AI hybrid models outperforms. If these models to be deployed on the clinic, FDA requires AI safety. This is an example of so-called non-inferiority test, which means that the combined model should not pose extra risk to the patients. So this is a little bit complicated. So the gray represent the behavior of the operative. So, and then you are not supposed to cross this line. That means that violating the safety of the patient. And the purple represent the behavior of the combined model that always lies within the safety zone, so then can be deployed. So in the interest of time, I'm going to stop. I'm happy to answer any question. Thank you.
Hi, everyone. Thank you for having me. My name is Jake Nudell. I am a bariatric and hernia surgeon, mostly here at Boston Medical Center. So as a surgeon, I have a confession. I don't know who my patients are. I don't know where they are along their clinical trajectories, and I'm not sure how to move them forward across clinical pathways to their ultimate goal. I can't answer those questions, but I believe we have the tools to do this very well using advanced analytics these days. And I would like to propose that we start to do this in a more robust way. So when I was a resident, we created a state transition model to look at who among those primary care patients at Boston Medical Center who was eligible for bariatric surgery got that surgery. There were several states in the model: a visit to a primary care physician, referral to a endocrinologist, endocrinology visit, referral to a bariatric surgery visit, and bariatric surgery. And from each state that I mentioned to every subsequent state in the model, we used advanced analytics to determine predictors for who would advance and why. These curves show who moved along the pathway, and that line at the bottom represents those who achieved bariatric surgery at the end, which is very few of them, about 2%. Using advanced Bayesian regressions, we could determine, for example, which of the primary care providers at Boston Medical Center referred to bariatric surgeons or medical weight loss specialists, and which clinics among the primary care clinics referred to obesity specialists. So if we drill down to the transition from showing up at a weight loss surgery clinic to getting weight loss surgery, that's the point at which I'm not sure who my patients honestly are. And I would like to start to track this, because in order to bend these kinds of curves that I showed on this slide, we need to understand what's going on with these patients live and at a population scale. So I'm starting to develop this software, which is an interface for enrolling patients into specific programs, like specific clinical trajectories, understanding who they are and where they are on their clinical pathways. When it comes to bariatric surgery, there are several things that people need to achieve. They need to have an initial intake, pick an operation. They may or may not get an endocrinology referral. They need TSH and A1C labs. They need to go through several dietitian group visits and one-on-one education. They need psychiatric clearance. And we have the tools now to automate and benchmark each of these using EMR data. We should be doing this. And it's very easy to see how such a system could eventually act autonomously to adjust patient flow and nudge people towards optimal outcomes. So if you're a clinician, I would like to work with you to develop these pathways and track your patients through an interface like this. And if you're a software engineer, I'd like to talk to you about developing the analytics and infrastructure necessary to generalize this system from bariatric surgery to various domains of medicine. Thank you.
Hi, good afternoon, and thank you for the opportunity to speak here today. So my name is Archana Venkatraman. I'm an associate professor in electrical and computer engineering on the Charles River campus. So today I'm just going to provide a brief snapshot of my lab and highlight a couple of projects that we're doing at the intersection of AI and neurosurgery. So just as a broad overview, my lab exists at the intersection of biomedical data, AI, and clinical neuroscience. So what we do is we develop new computational models and algorithms to try and harness the information in a variety of biomedical data sets to provide either better understanding or treatment options for neurological and psychiatric disorders. We work across what I call the application, the sort of translational spectrum, from addressing foundational and computational neuroscience questions to more translational, immediate translational applications of biomedical signal and imaging data to exploratory predictive analytics for healthcare. And all the while, we're addressing some key challenges in the space of neuroscience and neurosurgery, which are small data sets, extreme patient heterogeneity, interpretability, and just poor data quality control. So the two projects I want to highlight here today both involve identifying targets in the brain that are useful for neurosurgery in two different contexts. So the first context, which I'm showing on the left of the screen, is localizing eloquent cortex regions for preoperative planning. So if a patient requires a neurosurgery, so for example, removing a tumor, then it's really crucial for the neurosurgeon and the entire clinical team to identify areas of the brain that we don't want to damage, known as eloquent cortex. So by identifying eloquent cortex, we can find a safe resection pathway to actually perform the surgery. So eloquent cortex tends to be associated with the motor and language areas of the brain. Now, on the other side, the second project I'll highlight is the work we've done on epilepsy. So for epileptic patients who don't respond to drugs, our goal is to really determine where in the brain the seizure is originating so that potentially that area can be removed and the patient can become seizure-free. So with those two, so in both cases, we've developed deep learning or AI models to really tackle this challenge. So for the eloquent cortex localization model, what we've done is we've incorporated dynamic information from a modality known as resting state fMRI. So it allows you to track network patterns and organization in the brain. And this model that we've developed combines both spatial information and temporal information to provide maps in the brain of where key motor and language regions of the brain are. Really crucially, it actually can operate with missing data during training, so we don't need a complete data set for all patients. If some patients are just scanned for language paradigms and some patients are scanned for motor, we can handle that as well. And then we've evaluated on real-world clinical data for this resting state fMRI, and we showed that our model is actually able to localize these eloquent cortex regions. In fact, it's able to find bilateral patterns even when it's never seen that before. So, for epilepsy, we're doing a very similar exploration with this resting state fMRI. So once again, we're looking at network organization of the brain, and the idea is that the communication of the brain is disrupted by seizures. And so can we actually find that disrupted communication? And once again, we have developed a deep learning model using graph neural networks, and we folded in very strategic hypotheses and biological constraints, including the anatomical wiring of the brain, the fact that we want the seizures to be lateralized, and the fact that each subject will have different influences. We might have different scanners, et cetera, that we need to accommodate. And once again, we've evaluated this on real-world clinical data, and we're able to actually localize these seizure onsets in pediatric epilepsy cases. So both projects, I think, provide really fruitful opportunities for further collaboration and for trying to translate some of these technologies into a really challenging space of neurosurgery. Thank you.